Cool. Welcome to those of you who are starting online, watching this as a review. My name is Zach Brumbach. I'm TA 1553. This is the review for the third exam. Okay, so determinants. I honestly can never spell the word determinant right, but I'm an engineer, so it doesn't really matter. So a determinant, by definition, determines something, right? That's the whole motivation behind understanding determinants. Okay, what does a determinant determine? Does anybody have any idea? Yeah, that's one of the things it does do, but what it determines is it determines invertibility. Okay. Historically speaking, a determinant means it determines if you have a unique solution. Okay. So if the determinant of some matrix A is not equal to 0, that means A is invertible. Okay. Likewise, if the determinant of A is equal to 0, then A is not invertible. Okay. That's like the big overarching idea of determinants. And these will come up a lot more as you go further and further into math and calculus and engineering. These things are used in all kinds of different computer programs, but you don't need to know all that for the exam. So what do you need to know? How to calculate it, okay? There's two main different ways. The one that I prefer is cofactor expansion, okay? And there are a few different rules of determinants that are used to kind of shortcut all kinds of problems and things, okay? And if there are any questions at any point, raise your hand, interrupt me. This isn't meant to just be a lecture. It's meant to actually answer the questions you guys have, not just the questions I think you guys have. So there's a handful of determinant rules, and what they are is the determinant of A times B. See what the determinant of A times the determinant of B. Okay. With this rule, there's a little sub rule, which is the determinant of A raised to the power of n is equal to the determinant of A raised to the power of n. Okay, because this is determinant of A times determinant of A times dot dot dot, which just gets me back to this formula. So these are essentially the same rule, but different way we kind of think about them. Okay. Other rules we have is the determinant of A inverse is 1 over the determinant of A. Okay. The determinant of A transpose is just the determinant of A, bless you. And what a transpose is, it's when you flip rows and columns. Okay. Usually it'll just say AP. It's not raised to the power of T that defines a transpose. Okay. What am I missing? There's definitely more. Determinant of some number C times A is equal to C to the n times determinant of A. Okay, where A is n by n for all of these, you can't have a determinant that's not square. Okay, that doesn't even make sense because if something's not square, can it be invertible? Not a trick question. No, right? Has to be squared to be invertible. So if it isn't square, we don't even need a determinant to find out if it is invertible. Okay. Yeah, so these are the big ones, I believe. There's a couple more when actually doing like row reduction that apply and what that is. Someone correct me if I'm missing one, because I feel like there's usually one I miss when I do this. But when row reducing, if you multiply one row of A by some number C, then the determinant of what I'll call new A is equal to C times the determinant of A. Okay. And that's just C to the 1, not C to the n. That's just if we do change one row. Okay. And that kind of goes back to this rule because we're changing n rows with C to the power of n. That's why that happens there. The other rule is if we switch rows in A, then the determinant of our new A equals -1 times the determinant of A. Okay, any questions on any of these? Okay, cool. They're pretty straightforward, just kind of computational. It's not really a lot of theory here. One thing to note is one of the questions I know they asked on last semester's exam was like, given the determinant of A is 2 and the determinant of B is 4, find the determinant of A transpose times A squared times B to the -4th. Okay. Well, how you do this? You first break it up. Determinant of A transpose times determinant. This isn't exactly the same question, but that doesn't matter. Determinant of A squared times determinant of B to the -4. Okay. Excuse me. Determinant of A times determinant of A squared times 1 over the determinant of B to the 4th. Okay, so that's just applying these rules in a way that gets you to solve this whole headache to just be equal to set 8 over 4 to the 4th is 16 squared. That's 196, I think. Don't expect numbers that hard, but yeah, these are just how you apply these rules in like a traditional question. Okay. Is that number wrong? Is that right? 256? Did I do that wrong? Oh, you're definitely right. You're definitely right. I was doing 14. Whatever. ... Number. Okay. So those are the big parts of determinants. Okay. And another way they'll ask this would be like, given the determinant of A, B, C, D, E, F, G, H, I is equal to 5. What is the determinant of D, E, F, A minus 4D, B minus 4E, C minus 4F, G, H, I. So what is this equal to? Well, the things that don't really matter is when we add rows together, that doesn't change our determinant at all, okay? So we need to find our original rows in this set of rows here, okay? So the way that you can kind of see that this happened was we first switched the first 2 rows, and then we added the new first row to the second one, okay? So that we can get our original DEF, ABC, GHI, okay? Does that make sense? So the determinant of this is just -5, okay? Because adding any combination of other rows does nothing, okay? Any questions on any of this? Yeah. Yeah. So what you're usually looking for is it'll usually be hanging off a different row. Okay, they're not going to give you something where they jumble all 3 rows together. Okay. If they do, you need to just find each of your original rows. What I mean by that is this is one of our original rows. Check. This is one of our original rows. Check. So the only row left is A, B, C. Okay, so we look for what A, B, and C are here. Okay, for instance, if this was instead 2A, 2B, 2C, this would be -5 times 2 because that's how we change our original row. Okay, does that make sense? Cool. Other questions on this? Yeah.
So adding a row doesn't do anything.
Adding a row does nothing. I could waste my time and show you the whole proof for that, but I won't. If you want to know more about it or why, just Google it. Khan Academy has a video, I'm sure. So, okay, any other questions on determinants? Okay, the one other really big use we use for them is finding area or volume or some greater geometrical space. Okay. These questions are heavily favored. They really like asking them because it kind of ties a few different things together. So usually what they'll ask is given points 1, 2, 4, 5, and -1, -2. Find the triangle enclosed. Okay. So in 2D, what a determinant is on an actual graph, bless you, is, bless you, if we have just 2 vectors, okay, and we're trying to find the area here, okay, what we do is we add these 2 vectors together first, and we find the inside area, which is the determinant of A. where A is equal to vector 1, vector 2. Okay. And if we're just wanting to find this triangle or half of it, we just take half of whatever our determinant is. That's not right. So just write area equals 1/2 determinant of A. Can we have a negative area? No. You can just make it positive. Okay. So what we have for 3 given points, okay? If I plot these, I get 1, 2, 4, 5. That's gone. Okay, if I'm plotting these, we have 1, 2, 4, 5, and -1, -2. So something like this. Okay, so an incredibly skinny triangle. Okay. So how would I find the area of this? Well, what I could do is I could find a vector from here to here, and a vector from here to here, and half the determinant of that, of whatever those 2 vectors create. So the process to write that out, process to find area. How I like to write it is just pick a point, we'll call it point 3, subtract point 1, and this gives you your first vector. Okay. In this case, that's where we end minus where we start. So we're going from here to here. So that'll give me this vector. Okay. And then the second thing we do is we do the other point minus the same one that we used before. This gives me V2. Okay. This is just how you do it. You just subtract the points from each other in 2 different ways. And when you subtract 2 points together, you'll always get the vector between them. It doesn't matter which pair of vectors you pick for any of them. They just can't be the same. Like for one vector, you can't find the line here to here. For the second one finds from here to here. The area is going to be 0, right? It's the same vector. There's no area there. Okay. Any questions on this? Does this make sense? Okay, cool. What other questions do we have? Yeah.
The steady state vector, what is it? Can you explain the whole end behavior thing of that? Like, how?
Yes, I can.
Does not make sense.
Yeah, absolutely. So to talk about that, we need to start with talking about eigenvalues. Okay. Stochastic matrices are by definition matrices that have an eigenvalue of 1. Okay, and they're basically probability things. So I'll start with eigenvalues and walk all the way to stochastic matrices. Okay, yeah. Oh, I didn't calculate it. You can if you want. It's probably really small. Yeah, so to start with eigenvalues. At this point, the exam is in 2 days. If you want the whole explanation on why eigenvalues work, the whole shebang of everything that goes with it, I'm going to give an abbreviated version now, but there's a lot more behind this. So eigenvalues and eigenvectors are always found in the exact same way. Regardless if you're given a matrix, you do the same process, and you will always get eigenvalues, you will always get eigenvectors. Okay, eigenvalues, make that 100%. So how to find? You take the determinant of A minus lambda I, okay, because you call eigenvalues the Greek letter lambda, okay? And you set it equal to 0, okay? Solve for lambdas, okay? This is the definition of how to find eigenvalue. If you're given a matrix and they say find the eigenvalue, this is what you do, okay? There are a few tricks to get around this, but this will never get you wrong. This is the technical definition of how to calculate an eigenvalue, okay? Likewise, for eigenvectors, okay? And these don't have any fancy letters. We just call them V, okay? And these for how to find, it's always exactly the same process. Find a basis for the null space of A minus lambda I, okay? Find basis, okay? Now, what is an eigenvalue? Okay, eigenvalues and eigenvectors tie together so that they solve the equation some matrix times some non-zero vector is equal to just a number times that vector. Okay, so instead of doing matrix math, like say A is 10,000 by 10,000. That sucks to try and work out on the computer. Computers hate that. Okay, what we do instead is we can just break it down into its eigenvectors, find them, and multiply by a singular number instead. Okay, it makes life much, much easier, and that's why we like to do eigenvalues. Okay, so both of these equations are derived from this initial condition. Okay, and to always check yourself when you find an eigenvector, if you have the time, you can multiply A times that vector, and it'll spit you out lambda times your vector, and that should be your check. Okay. So another thing to note is how for like the last exam did we write A times V instead? How else did we say that? Yeah, exactly. T of V in this case, right? So don't get tripped up if they say T of V is equal to lambda V. Okay. Or something else that we really, really like about these equations in particular is when we raise A cubed, we just get lambda cubed, okay? Or we do the transformation 3 times, okay? These all mean the same thing, okay? Don't get confused just because you see a slightly different notation that you already know, okay? All right. So some other facts about eigenvalues. The trace, so your determinant first of A will always be equal to the product of your lambdas. Okay. I don't want to write the word product every time I talk about this, so I just write a capital Pi, just the same as like a summation for sum. Okay, capital Pi means product. Okay. So, for example, if my lambdas are 2, 4, and 8, now I'll do easier numbers, 1, 1, and 2, what is my determinant? 2. If you have eigenvalues of 0, 1, and 10, what is your determinant? Is it invertible? No. So that kind of goes with the motivation behind. If lambda equals 0 is an eigenvalue, then our determinant is 0, it's not invertible. Okay. Those two mean the same thing. Having an eigenvalue 0 means the determinant is 0. Okay, that's how those two go together. Yeah.
Is that even if A is bigger than its
Yeah, always true. Okay. And one thing to note is you must count multiplicity. Okay, so if, for example, we have a matrix A that has lambdas equal to 2, multiplicity 3, and 1, multiplicity 1. Okay, and the way we get these multiplicities, just to backtrack, is here. Okay, we call this here our characteristic polynomial. All right. And what we'll always be able to do is we're finding zeros for it because we set it equal to 0, right? That's where we get our lambdas. And when we factor this out, we'll always get something that looks like lambda minus 2 cubed, lambda minus 1. Okay. Equals 0. This is just some example matrix. Okay, nothing. So what this means is we have a lambda equals 2, and we have a lambda equals 1. Those are our eigenvalues. But this one pops up 3 times. That power is our algebraic multiplicity. Okay. Algebra talks about numbers. Okay. Geometry talks about space or vectors. Okay. That's the big distinction between the two. Okay. Algebra, numbers, geometry, vectors. All right. So we'll talk about that when I talk about vectors in a second. But so when we get here, for instance, what is my determinant of this matrix? No. 8. Because we have 2 3 times, so it's 2 times 2 times 2 times 1. Okay, that's kind of how you have to put those two things together. Okay, that's why multiplicity matters. All right. Yeah. Yes, you will. I'll get to that in one moment. So, any other questions on eigenvalues? Is like a thing right now. A really, really easy way to always find eigenvalues is if you're given a triangular matrix, which what that looks like is number. You have numbers on all your diagonal, okay? And everything below it is 0 or above it is 0. So you can draw a nice triangle. Okay, we call this a triangular matrix. And then these numbers on the diagonal are eigenvalues. Okay, you can pull it off really, really easily if they give you a matrix like this. Okay, Eigenvectors are a little bit more complicated, okay? So when we talk about eigenvectors, okay, eigenvectors, like I said, they're always the basis for the null of A minus lambda I, okay? So before we can find this, do we know that A minus lambda I has a null space for our lambdas we found? Why? How did we solve our lambdas? We found the determinant to be 0, the determinant of A minus lambda I to be 0, right? So if this determinant is 0, is this invertible? No, it's not invertible. Does it have a null space? Yes. Okay. So we find these lambdas such that this will be fixed. Okay, that's the idea behind eigenvectors. That's why we find it. So from here, like I said, your basis is always equal to your eigenvectors, right? Okay. So your number of eigenvectors is always equal to the dimension of null of A minus lambda I. Okay. Does this make sense, right? If we have a null space of A minus lambda I, what's the shape of the null space? It's R to the number of what? Free variables in R to the number of columns. Good. Yeah, so what we're looking for essentially is how many free variables does A minus lambda I have? Okay. If you can find that, then you know your number of eigenvectors, okay? So going on this is something we learned last exam, right? How to find the basis of a matrix, okay? And just as a little sidebar, if A is 1, 2, 2, 1, A minus lambda I is just equal to 1 minus lambda, 2, 2, 1 minus lambda. It's just subtracting from that diagonal, okay? Just to see that written out properly, okay? Okay. So why do we care about eigenvectors? Well, for this exam, for one, fastest class. For two, what we really like to do with eigenvectors is we like to decompose a matrix A in terms of its eigenvectors. We call that eigendecomposition, or for this class, we call that diagonalization, okay? Diagonalization, if you look it up, it's just called eigendecomposition for a square matrix, okay? So what we do is for diagonalization, for this to be true, you must always be able to find a C and a D such that A equals C, D, C inverse, right? So what that means is we define D as a diagonal matrix with lambdas on diagonal. Okay. Just to backtrack for a second. When we have something that looks like this for a characteristic polynomial, okay, we will always have as many eigenvalues as we do n, rows or columns, okay? So this matrix here, how many eigenvalues does it have total, including multiplicity? So A is A, 4 by 4, okay? So you will always have as many eigenvalues as you have n, okay? Always, always, always. So you'll always be able to make D. So this is always possible. Smiley face. Okay. D isn't the problem. The problem is C. C is a square matrix with corresponding columns equal to your eigenvectors. Okay. So if, like we just said, if A was 4 by 4, okay, let's make our D for this matrix. So we have 2, 2, 2, 1, with zeros everywhere else. I usually just write a big 0 to save myself some time. And C is going to line up. So we have vector 1, vector 2, vector 3, and vector 4. Okay, and these correspond to these eigenvalues. Okay. So to go back for 1 second, we said that this must always exist. The null space of A minus lambda I must always exist if we found our lambdas properly, right? So how many free variables must this have at least? 1, right? We found its determinant to be 0. We found it's not invertible. This will always have at least 1 free variable, which means it will always have at least 1 eigenvector, okay? We'll always have as many eigenvectors as we do number of free variables, okay? So, do we know we can find a V4? Yes, right? We'll always be able to find at least 1 eigenvector. Otherwise, that eigenvalue doesn't make sense. It doesn't satisfy A times V equals lambda V, okay? The problem is when we have repeats, okay? So here we have 2 happen 3 times. We need to find 3 different vectors that satisfy that. 3 linearly independent vectors, okay? Because they come from the basis of A minus lambda I. You cannot forget that these 3 things must come from a basis and they must be linearly independent, okay? That's not to say that you can't change them a little bit. For instance, if I give you 1, 0, 0, 0, 0, 1, 0, 0, and 0, 0, 1, 0 for your eigenvectors for lambda equals 2. Something else that's totally valid would be 4, 0, 0, 0, 0, 10, 0, 0, 0. Oh, that's one too many. And 0, 0, negative E 0, where E is 2.1, whatever. Okay. So are these 3 things still linearly independent? Do they span the same as this? So they are still eigenvectors, okay? They still form the same basis, so they're just as valid to put in the C. The reason this doesn't matter is because what we do is we multiply by C inverse, and this will cancel out whatever choice you make to just kind of make it easy, okay? So you have to do a little bit less thinking, which is nice. Okay, going back to this. We need to be able to make C, so we need these 3 vectors, right? So how many eigenvectors do I need? 2, 3. What does my dimension of my null space of A minus 2i have to be for this to be diagonalizable? 3, right? We need to have 3 vectors, so that needs to have a dimension of 3, okay? So diagonalization happens when you have enough eigenvectors to fill this, okay? That's kind of what it boils down to. Let me move this a little bit. Happens only when you have n linearly independent eigenvectors. Parentheses, your algebraic multiplicity is equal to geometric multiplicity for all lambdas, okay? So what did we say our algebraic multiplicity was for 2? 3, okay? So how many vectors do we need to make it diagonalizable? 3, right? So how many vectors that eigenvalue has is called geometric multiplicity. Geometric multiplicity just means how many eigenvectors go with it that are linearly independent, okay? Dimension of eigenspace, okay? Eigenspace is just that null of A minus lambda I, okay? It's just a term that means null space, okay? Okay, any questions on any of this? Yeah. Yes, that's exactly right. It's how many vectors you get for that value, okay? One other little sidebar to have is, like I said, that the determinant of A is equal to the product of my lambdas. I forgot to mention that the trace of A is equal to the sum of your lambdas, okay? And what the trace is the sum of your main diagonal, okay? So I have a matrix that looks like 3, 4, 1, 2, okay? What's my trace here? Oh, shit. My trace is sum of your main diagonal, 3 plus 2, 5.
The lambdas or
So the trace is the sum of these two, okay, which is equal to the sum of 2 other numbers. Okay, so what this means is I could have a lambda. So my trace of A is equal to 5, which is equal to lambda 1 plus lambda 2, right? Sum of your lambdas. But that doesn't tell us if it's 6 minus 1, 7 minus 2, 5 minus 0. We don't know what these two numbers are at all. Okay, we just know that they add to be 5. Does that make sense? Okay. Any other questions on any of this so far? Another quick little shortcut, just as a sidebar, is for a 2 by 2, the characteristic polynomial is always lambda squared minus the trace of A, lambda plus the determinant of A. Okay. If you don't want to work out the math, you can just skip to this part if it's a 2 by 2. Okay. For any n by n characteristic polynomial, okay, it's minus lambda to the n plus unhappy numbers. And then it always ends with the trace of A times lambda plus the determinant of A. So if they give you a characteristic polynomial, you know your determinant. Okay. So whatever size this ugly thing is, it'll always end with this determinant of A. So if they give you a giant equation that starts with a lambda to the 10 and it ends with plus 2, the determinant is 2. Okay. Does that make sense? Okay. Yeah. 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 Yes. Last year I made the mistake for the 3rd exam and I told my students, oh, they won't make you find the eigenvalues of a 3 by 3 matrix. That's evil. And it was. It was a pain in the ass to grade, but it's fine. That is kind of the worst case scenario, okay? Usually if they give you some kind of big matrix, okay, there's tricks to determine if it's determined to 0, okay? Determined to 0 if it's not invertible, if any rows or columns are the same. But it's the exact same process. Find the determinant of A minus lambda I, factor it out, find the null space of each of your A minus lambda I's, okay? Does that make sense? That's what I mean by it's very like algorithmic. Okay, it's the same 2 things over and over to find eigenvalues to eigenvectors. And you can find complex numbers from that as well. Okay. Those pop out every now and then, which is a big sad face, but yeah. Yep. Yep. So for 3 by 3, it'd be minus lambda cubed plus sad face lambda squared, because that number is not very easy, minus the trace of A times lambda plus the determinant of A. So that's a good example of like, hey, this is a little bigger. This number is a big headache. Okay. But everything else comes kind of straightforward like that. Okay. All right. Fairness. So that's everything but stochastic matrices, which is where this question originated. So any other questions on any of this before we move forward? All right, cool. So stochastic matrices are when we put probability with linear algebra. Okay. So the way we always draw stochastic matrices, just to show it, is it's a matrix of probabilities. Okay. So what must your probabilities always sum to? 100% or the number 1, right? So is that rows or columns? Columns. Your columns must always sum to 1. Rule number 1, columns sum to 1. Okay. Can I have any values greater than 1 or less than 0? Can you have a percent that's less than 0? Can you have a fraction that's greater than 1 in a probability context? No. All numbers are between 0 and 1. Okay. So How do you find a stochastic matrix would be the first question. Usually they give you a long-winded word problem that just ends with some numbers in a matrix, okay? So numbers in a matrix, the way I always write stochastic matrices is I start at start. I write that above my matrix every single time, and I write end to the left of my matrix, okay? And I draw this little line. You don't need to do that, but that pops out in electrical engineering a lot, so that's why I do that. So these columns correspond to where I start. These rows correspond to where I end, okay? So in a very simplistic example, say there are 3 bars that do trivia on Wednesdays, okay? And each of them go back and forth on how a certain group of people go each Wednesday to determine where to go, okay? So let's say if one week you were at bar A, there's a 50% chance you go back. There's, that was too far. There's a 30% chance you go to B the second week, and there's a 20% chance you go to C the second week, okay? For B, nobody sticks around at B. 50% go to C, and 50% go to A, okay? For C, let's say 70% of people stick around, and the other 30% go to B for some reason, okay? So this is like how you draw a diagram for stochastic matrix, okay? It's this gross little bubble of like who goes where based on what, okay? And this is like per unit time, so like per week or per year or per whatever, okay? So to make a matrix from this, what we do is I always write my 3 things, okay? A, B, C, and A, B, and C, okay? So what goes in this position here is how many people start at A and end in A, okay? So this is 0.5, okay? How many people start at A and end at B? 0.3. So what is this entry at the bottom? Well, you don't even have to look at the thing. You just know it's 0.2 because you have to sum to 100%. Okay. Likewise, how many people start at B and end at B? 0. And then 0.5 go to A, 0.5 go to C. For C, 0.7 stick around, and 0.3 go to B, and none go to A. Okay, this is how you would fill in a stochastic matrix based on a word problem. Are there any questions on how to do this? Okay, so this is how we shift every unit time, every day or week, okay? As we do this infinitely many times, we're going to approach something, okay? We're going to approach what we call the steady state vector, all right? And it's how things end up over time. Like the way we see this, that you may have seen this before, is in calculus, which I know, whatever, but like we have a graph, right? And we have these lovely vector fields that we've drawn before, right? And maybe all of these things end with something that just goes like this, okay? So what this looks like is if I start here, I move here. If I start here, I move here. I start here, I move here, okay? What we would call is this point that all things approach is we would call the steady state, okay? Doesn't matter where you start, you will always end up here. That's the idea of the steady state. As time goes on forever, you will approach something. Stochastic matrices, by definition, have a steady state vector, okay? Something has to happen as you go to infinity. There has to be some balance you can have, all right? So, how do we find it? Well, there's one other really important fact of stochastic matrices, and that's that they always have lambda equals 1, okay? And if they always have lambda equals 1, does that mean they have an eigenvector for lambda equals 1? Yes, you have a value, you must have a vector at least, okay? At least 1. This implies there exists a vector such that A times vector equals just your vector, right? So by definition of this, we have some vector that when we multiply by stochastic matrix, it's the same thing. Called steady state. This doesn't change as we do more, as we add more time to it. Okay. All right. So now we've arrived at finding an eigenvector. How do we do that? I hear some low groaning. Is anybody confident in it? Yes, subtract 1 from the diagonal and do what? Find the null space, okay? So we have to find lambda equals 1 eigenspace, which is just basis for null of a minus 1i, okay? This is how you do it. This is the process, all right? So one other thing to kind of note is if we have a times our initial vector and we go to n, as we go to infinity, okay? What we're gonna have is we're gonna have our total number total, times v steady state, okay? Because steady state is a vector of probabilities. The probability you end up somewhere as time goes to infinity, okay? So it does, I'm gonna call this vi just to distinguish it. This is our initial vector, all right? So this is a pretty straightforward process. To find a to the n times any vector, what you have to do is you have to find the total number of people, population, users, whatever, and multiply by the steady state vector, okay? So I said that the steady state vector you find, I'll write this as find v steady state. Okay, find the one eigenspace, find the basis for null of a minus 1i. Okay, there's one extra step we have to do. Okay, let's say I find this basis and I get myself the numbers 3, 2. Okay, are these probabilities? No. What is their sum? 5, right? It's not 1. How do we get it to be equal to 1? Yeah. So we just turn this into 1 over 3 plus 2 times 3, 2. And this gives us v steady state, which in this case is 3/5, 2/5. You don't need to write in decimal for this exam. If you want to keep it in fractions, you are absolutely welcome to. In the off chance you get ugly numbers, sometimes that pops out, and that sucks. Maybe you find a basis for a, 1 minus I, and you get, I mean like disgusting numbers, like 17 over 101 or something just, bleh. Sometimes that happens and that's okay. All right, just don't panic if you see stuff like that. I don't know what the exam looks like, so I'm just telling you not to freak out if that happens, but that's not him. I actually don't see the exams. Okay. So for example, if this is my steady state vector and I say my v initial is 70, 80, okay? This is where I start. This is not where I end. This is not what happens as I take a to the n times 70, 80, okay? What we said this is equal to, it's equal to the total population. What is my total population of this vector? What is my sum of this vector? 70, 80. 70 plus 80, which is 150, right? Times 3/5, 2/5. Okay. Which gives you whatever it gives you. Cool. Any questions on this? Okay. That is all the conceptual stuff of this exam. So now let's move into some actual problems, some computation stuff. What questions do we have? Yeah. Oh, I can. There's one from one of the supplements that I liked. Let me find that one really quick. 102030204. Nah. Okay, here we go. So say they asked to find the determinant of this, okay? If you were to Google the determinant of a 3×3, there is an equation you can memorize, but it has a bunch of terms, okay? All right. So to work something out with cofactor expansion, all right, what we need to do is step 1 is always draw what I call the plus minus matrix. Okay. And what this is I draw my exact same size matrix, but I put a plus in the top. And then I put a minus, and then I put pluses, then I put minuses, and then I put a plus. Okay? So it's literally just always plus in the top right, and then we alternate diagonals all the way down. Okay. And why I do this is because we can pick any row or column to find the determinant. So what is an easy row or column I can pick here to move along that has a lot of zeros? Second row, second column, same thing. Okay. So I'll pick the second column for no particular reason. Okay. So the way we do cofactor expansion is I take this number here, that's first 0. All right. I multiply it by, or I put it in front of either a plus or a minus. It's on this matrix. And then I multiply by whatever is not the determinant of whatever is not in that row or column. Okay. So the first thing in this would be, it's going to be minus 0, the determinant of whatever is not in my column or row. So I'm left with 0, 0, 2, 6. Okay. And then we move to the next position. Okay. Which is this number 3. So it was a plus. So now we have plus 3 determinant of what we call our minor. Okay. And our minor just means the things that are in that row or column. So this is 1, 2, 2, 6. And lastly, we have to go across the entire column or row. And it doesn't really matter because it's minus 0. But times determinant of 1, 2, 0, 0. Okay. Obviously, this is 0, and obviously this is 0. That's why we picked this column. Okay. We picked this column because it had zeros, so that when we expand it out, the first would be times 0 and the last would be times 0. Okay. So from here, let's go to 3, determinant of 1, 2, 2, 6. What is the determinant of a 2 by 2 matrix? Bless you. AD minus BC. Okay. So this is equal to 3 times 1 times 6 minus 4, 2 times 2. Okay. So this is equal to 3 times 2, which is equal to 6. Okay. Make sense? Lovely. Is this matrix invertible? Why? Because the determinant isn't 0. Exactly. Okay. If this matrix has eigenvalues of 1 and 2, what is its third eigenvalue? 3. Why? Right. This is our determinant. This is the product of my eigenvalues. Okay. If I'm given to have an eigenvalue of 1, an eigenvalue of 2, my third eigenvalue must be 3 to multiply together to be 6. Okay. Any questions on any of that? Yeah.
So if like our two of the eigenvalues are 2, find out 4 times.
Yep. So in this case, if I gave you, you have an eigenvalue equal to 2 with the multiplicity of 2. What is my third eigenvalue? Not 2. Not that hard of decimal math. 1.5. Promise I wouldn't give you anything too gross, but yes. 2 times 2 times c equals 6. 4 times c equals 6. C equals 6 points. 3 halves. 1.5. Yeah. Sure.
If you're asking to find a diagonal matrix, you find C first, do you have to multiply 3 of them together, or can you read it out?
Well, if you're given a matrix A and then you say to diagonalize it, find CDC inverse, and you multiply them out, what are you going to get?
What would be X?
They would have to specify. It would be very clear. If it says diagonalize, that means find CDC inverse. It doesn't mean find A. Okay. All right. One other thing Okay. One other big thing that people really confuse on this is complex eigenvalues. Okay. Complex eigenvalues are a really big deal. Okay. Why they're a big deal is because they use complex numbers. And for those of you who study engineering or music tech or any kind of like signal studies, that's going to pop up vibrations, voltages, currents, any kind of wave or wind or fluid or anything, you're going to see a lot of complex. Okay. What a complex number is it makes life with this math easier, contrary to what you might believe. Okay. How many of you know what a complex number is? Okay, someone define it for me. Okay, that's not a definition. Okay, square root of -1 is why? Why do we call it I? What does that do for us? This is something that not a lot of people know, and especially when you get to upper level classes, it comes at your detriment if you don't understand it. So that's why I'm here explaining it to you. Okay. What a complex number is it is a number that carries both a magnitude and phase. It is essentially a vector as a number. Okay. So if I have, for example, the easiest way to show this is just a graph to build intuition for what complex numbers are. Okay. So if I have a graph of a sine wave that looks like this. Okay. It has an amplitude that looks like this and a phase that's this far off, right? I'll call this phase like a theta. Okay. So the way we like to write this in engineering is say this magnitude's 4 and the angle is 30 degrees. Okay. We like to write this as 4 angled theta. Okay. 4 angle 30. We can rewrite this as 4 cosine of 30 plus I 4 sine of 30. Okay. We use I because I tells us that there's a phase. There's some kind of difference in rotation, angle, anything like that. So if a matrix has an imaginary or a complex eigenvalue, what does that tell you about that matrix? What is it doing, at least a little bit? Rotating. It's turning, right? Because there's some angle to it. If you have a complex eigenvalue, that means you're rotating to some degree. It doesn't necessarily mean it's a perfect angle, okay? But because it could scale and then turn and then reflect, it could do all kinds of stuff. But that just tells you that somewhere in there, you're rotating, okay? That's what complex numbers mean. Complex numbers mean rotation. It means a delay. It means some kind of signal. It means any kind of thing like that. Okay, that's why we use I. Or if you're engineering, you're going to stop using I, you're going to start using J. because. You're also going to stop using lambda and start using S. But that's not for this class. Okay, so this is what a complex number is. So for a rotation matrix, for a projection, and for a reflection, these are the big three that they really like to ask about on this exam. Okay, just a quick yes, no question. Okay, these three are very well defined in terms of eigenvalues, diagonalization, and invertibility. Okay, one other little sidebar: invertibility, diagonalization, totally separate things. The only time they overlap is if you have a lambda equals 0. That means we have an eigenvalue of 0 that helps us with diagonalization. Doesn't mean it's diagonalizable. Does mean that it's not invertible though. Okay. So on these, they all have eigenvalues that are very well defined. Okay. So we'll start at the bottom. If we're reflecting over something, what are my eigenvalues? 1 and -1. Okay, because you can think about this geometrically. If we draw this graph, okay, here is the line we're reflecting over. Okay, if I sit on this line, what happens as I reflect over it? Nothing. How do we write that in terms of multiplication? Times 1. Okay, what if I'm sticking straight off of the line? What happens as I reflect over it? You become exactly your opposite, right? So that's why this corresponds to lambda equals -1. Huh. And this equals lambda equals, this corresponds to lambda equals 1. Right? So, is a reflection invertible? Can you undo reflecting over something? Yeah, right? Is a reflection diagonalizable? Also yes, right? You're either, like, if this is in 3D and you're reflecting over a plane, okay? How many vectors make up this plane? 3. Planes. We're in 3 space, but it is a plane in 3 space. 2 linearly independent vectors make that plane. We have 2 eigenvectors. And then for the one sticking straight off, we have one additional vector that sums to 3 vectors total. We're in 3 space, that's 3 vectors, diagonalizable. Okay. Projections always have eigenvalues of 1 and 0. They are also always diagonalizable. Okay. It's exactly the same thing here. Okay, but this is no longer -1. It's now 0. Instead of flipping, it just gets squashed. Okay. Is this invertible? Why? Yeah, the determinant is 0. The product of these two are 0. Or you have lambda equals 0 as an eigenvalue. Okay. All right. Lastly, for rotations, complex with 2 exceptions. Theta equals 180 and theta equals 0. What happens to you if you reflect 0 degrees? Or you rotate 0 degrees? Nothing. It's the same thing. Not a dumb question, I promise. But as you go up, like rotating by 360 degrees gets really complicated. But nevertheless, for lambda equals 0, or for theta equals 0, we have lambda equals 1. And for lambda equals 180, it's just equal to -1. Both are still invertible. Both are diagonalizable. Okay. Rotations, these are always complex. So will they always multiply to be a number that's not 0? For the sake of this, yes, because they come in conjugate pairs. Okay. And what you'll see is you'll see them to be like 1/√2 plus I 1/√2. If anyone wants to take a stab at it, what angle is this? 45 degrees. Okay. So we could rewrite this in what is called phasor form as 1 with an angle of 45 degrees. That's why we use I. Okay, it has an angle and a number. That's why we care. Okay, makes sense. If it's anything more complicated than that, like if it was instead 1 plus 1i, okay, now the magnitude is √2 angle 45 or whatever, right? That's just your eigen. Okay. Or that's what we would rewrite. Yeah, not too important for this class, but I think it's cool and it's more applicable as you go further up to know these things. Okay. Okay. Can you always undo a rotation? Yes, that's another way to think about how it's invertible. Okay. All right, other questions we have. Yeah.
The sample material 3A,
I can pull it up.
problem 7A. You talked about like
Yeah, sorry, give me 1 second. I just typed in Jankowski and a baseball player pulled up. It's the first time that's happened. 5A, sorry, 3A. Question or midterm 3A.
oh yeah.
Okay. 7A.
Yeah.
Okay. All righty.
So what was that last column?
Oh, Jesus fucking Christ. All righty.
That.
Yeah.
Diagonal.
Yes. Rotations are always diagonalizable as well. All righty. So this is the question that's a much more complicated expansion on our determinant rules. Okay. So we know that a determinant with just these rows is 18. So what we're asking is the determinant of this giant matrix with a new column. Okay. Ew. I haven't looked at these yet, but all righty. What is this? All right, so what you're supposed to do here, supposed to recognize that there's a lot of things to think on. First. Second of all, what's the biggest addition here? What's the new thing we're adding? It's a new column, new row. All right. Some little sidebar here is you can have a matrix made of other matrices. Okay. And if you are a mechanical engineer, you will see this a lot. So what you have is you can have a matrix like we'll call it M. And we can have a matrix A with a bunch of zeros down here and a bunch of zeros over here, and then another matrix B. You can have a matrix made of matrices. That's fine. Okay. And basically what you're supposed to look at in this question, all right, you're supposed to see some fucked up version of what we started with, and then the addition of a new row which has -2. Okay. So what we need to do is we'll break this up and we'll say -2 times the determinant of 3a plus 2b, c, b, 3d plus 2e, f, e, g plus 2h, k, h. Okay. So now the question is, how on earth do we get from here to here, right? Now we're combining a column. All right. So I know he has the solution and everything worked out, right? But this is the hardest example of a kind of determinant of a matrix could be, like actually. Okay, I know this problem sucks, and that's because it's made to suck. All right. Okay. So which way would you like to try and go? This way or this way? Let's start here. Okay. Is that okay? Does anybody want to do anything else? So what we're trying to do is trying to use matrix rules to get from disgusting thing to just the number 18, some other stuff. Okay. So what do you notice about the first column? Is this a legal thing we can do? Can we add columns to other columns? No, right? So how do we change that? How do we get from columns to rows? Sure. We transpose it, we switch them, right? All right, so what I'm doing here is I'm going to do these matrix steps and I'm going to multiply by what I change each time, okay? So now it's going to be -2 times the determinant. Sorry. What do we multiply the determinant by when we take the transpose? 1, nothing, right? Determinant of 3a plus 2b, 3d plus 2e, g plus 2h, c, f, k, b, e, h. All right. So now what do we see? Is this something that we can get from our original matrix pretty easily? Ish. Is there anything that maybe we can cancel out a little easier? Yeah. Okay. Yeah. Three G. Right. So what's something we can get rid of here? Yeah. How do we get rid of it?
Or like, you don't.
We don't need to do anything to determine it, but how do we get rid of that? We just subtract this row times 2, right? Okay. So I'm going to write this as row 1 equals row 1 minus 2 row 2. What does this do to my determinant? Nothing. All right. So now we're here. We need to get to that original matrix, okay? So let me remind you that the determinant of A, B, is that ABC? Yeah. A, B, C, D, E, F, G. How do they write that? Oh, G, H, K. They skipped I and J because they're imaginary numbers and people don't like putting them in there. I'm actually serious there. They actually usually like skipping E as well, but and C, a lot of numbers are just taken up by constants. Actually, in like fun little sidebar, in like recent math history, we've ran out of English, Greek, and Cyrillic letters, and now they're moving to some weird languages for really high level math, but whatever. So we're trying to get here is equal to 18, right? How do we get from this matrix to this matrix? Well, what do we notice about the first row? What happens to it? Well, the first row is not the first row, right? So maybe what's something that we can look at a little differently here compared to that? We can look at its transpose, right? Because the determinant of instead A, D, G, B, E, H, C, F, K is equal to 18. We're just trying to get this in forms that look easier, okay? And as a rule of thumb, you see a column multiplied by a number, just change it. You do row. Okay, for a determinant question like this, at least. All right. So now, how do we go from this matrix up here to this matrix down here? What happens between them? Yep, we scaled the first row by 3 from here to here, right? So -2 times 1 times 1 times 3 times the determinant of A, D, G, C, F, K, B, E, H. Now what's the last thing we got to do? Swap these two rows, right? And then we have our lovely number 18 there. Okay. It's equal to -2 times 1 times 1 times 3 times -1 times the determinant of our original matrix, which is 18, which is equal to 6 times 18, which is some gross number that I don't really want to work out. 108. Someone correct me on that if I'm wrong.
Moving 1/3 instead of 3 years.
Huh?
So why didn't 3 instead of 1/3? Just keep on down.
Yeah, it's good going backwards. Yeah, sorry. Any questions on this? Yeah.
We can get rid of the last column. We good. There was like a.
Yes. The way we can do that is because we see our branch of our matrix, okay? And we can just consider if this was any other row, it would suck. Okay, but since we have all zeros, okay, what happens is we can look at this matrix as its own thing, and we can look at something separate over here as its own multiplier, okay? So essentially we're looking at two separate pieces, okay? Does that kind of make sense? Okay, basically, if you see like a row of zeros or whatever else behind it, like if instead this is a 5, 5, 5, there's -2, 0, 0, 1, or 0, 2, you instead multiply by -4, which is the determinant of what's down here. Does that make sense? Okay, cool. Any other questions on this? Yeah. Yeah, sure. Any other questions on this? Okay, yeah, go ahead. Uh-huh. Which quiz? Okay. Let me pull that up really quick. Which number was it? Number 4. So it's asking what are the eigenvalues in A of 1, 3? Okay, just making sure I have the right one. So what we have here is we have CDC inverse, right? Now you know this form, right? Matrix, diagonal matrix, matrix inverse. Okay. So if it asks, what are the eigenvalues of A? Well, we have D, right? So what are my two eigenvalues? 4, -2, exactly. Okay. What are my eigenvectors here? Remember what C corresponds to? C is our eigenvectors, right? So Is this an eigenvector?
Yes.
Is this an eigenvector? Yes. Okay, so your two eigenvectors are 1, 3, and negative 4, 2. What eigenvalue does 1, 3 correspond to?
4.
Why? It's in the same column. Exactly. This is the first column. This is the first column. What does this vector correspond to? Which value? Yep. So if 1, 1, 3 is an eigenvector, then we can rewrite this as, oh, that's not a 3. I got ahead of myself. We can rewrite this as 4 times 1, 3, right? Because it's just an eigenvector for lambda equals 4. So it gives me 412. Does that make sense? It's a big O moment there. Yeah.
So what is the eigenvalue?
Yeah.
But why A?
Well, we define eigenvalues as A times some vector equals lambda times that vector, right? If V is an eigenvector. And we found, is this an eigenvector?
Yes.
Yes. For what eigenvalue?
The very
4. Right? So A times V is equal to lambda times. Does that make sense? Any other questions on this one? Yeah.
Why are you going to the negative?
Because this vector corresponds to this column where 4 is. Okay. Questions on this? Yeah. That is a fantastic question. That's actually why we do diagonalization. Okay. We do diagonalization because instead, if they ask me what is A of negative 3, 5, okay, this sucks. We don't know what A is, and I don't really want to multiply a 2 by 2 by a 2 by 2 by the inverse of a 2 by 2. Okay. So what we can do instead, if it's diagonalizable, we can always break up vectors into parts that are eigenvectors instead. Okay. Because if this is diagonalizable, how many vectors do I have? 2 in this case, or n, right? If I have n vectors, n eigenvectors, it's diagonalizable. And, well, if I have n eigenvectors, and by definition, they're all linearly independent, what do all of my eigenvectors span? All of Rn, right? If n linearly independent things, they span everywhere. Okay, that's what diagonalization means. It means my eigenvectors, when we combine them in different ways, will touch everything. Okay. So since this matrix is diagonalizable, we can rewrite this as A times, or let me sidebar this first. We can instead rewrite negative 3, 5 as a combination of C1 times 1, 3 plus C2 times negative 4, 2. Okay. This might also come in the form of like, what is T of negative 7, 7? Okay. Just like any kind of thing like this, this is always the process. Okay. To find C1 and C2, what we always do is 1, 3, negative 4, 2, augmented with negative 3, 5, right? This is my column for C1, this is my column for C2, this is my number column, okay? And this is going to row reduce to give me 1, 1 in this particular case, okay? So that means I can rewrite this as A times 1 times A of 1 times 1, 3 plus 1 times negative 4, 2. Okay, which then this is equal to A of 1, 3 plus A of negative 4, 2, which is equal to 4 times 1, 3 minus 2 times negative 4, 2, which is equal to, we said it was 4, 12 plus 8, negative 4, which is equal to 12, 8. Okay, does that make sense? What you could do is, if you really wanted to, you can do this. You can multiply this out. Something they might ask is, what about A to the, oh God, what about A to the 8th of this? Okay, now you have to multiply 2 by 2 by 8 2 by 2s by another 2 by 2. Okay, what you can do instead is we work out the same problem, but we get 2 apart, where this is just to the 8th and to the 8th. Okay, so multiplying numbers by these things instead. Okay, exact same process. This power just kind of dissipates, or it kind of separates like that. Okay, and then equals ... Okay, does that make sense? Okay, yeah.
Oh, where did the foreign?
The 4 and -2 came from what my eigenvalues were for those vectors. Okay. And whenever we solve like a matrix like this, okay, these must always be your eigenvectors. All right, they can't be anything else. Okay. Questions on this? Yeah. Yeah, absolutely. Okay. So if I start with A of some vector that isn't an eigenvector and A is diagonalized, if I have CDC inverse, for instance, okay, what we can do is we can break up this vector into components that are eigenvectors. So instead of having to do matrix math, we can multiply by constants. Okay. So now this time, let's take T of -7, +7. Okay. Do we know that we can break up -7, +7 into eigenvectors? We do. What is my span of my eigenvectors? R2 in this case, right? So if it spans all of R2, can I hit -7, +7? Sure, why not? Okay, to solve that, we always augment 1, 3, -4, 2, augmented with, in this case, -7, +7. How do I solve this? Row reduce. Spoiler alert, it's 1, 0, 0, 1. Nope, 0, 1, 1, 2. Okay. So from here, okay, let me move this other stuff out of the way. Let me just move this down. Okay, so we're here, and we know -7, +7 is equal to, we said it was 1 times 1, 3, plus 2 times, what was my other vector? -4, 2. Okay. So T of -7, +7 is equal to T of 1 times 1, 3 plus 2 times -4, 2. Okay. And since this is linear, since this is the subspace, because we're doing linear algebra, we can rewrite this as T of 1 times 1, 3 plus T of 2 times -4, 2. Okay. Just quadruple checking. So from here, we can rewrite this as 1 times T of 1, 3 plus 2 times T of -4, 2. All right. And if 1, 3 is an eigenvector corresponding to lambda equals 4, what is T of 1, 3? 1 times 4 times 1, 3. Okay. Likewise, if -4, 2 is an eigenvector corresponding to lambda equals -2, what is the transformation of -4, 2? Yeah, I think I heard that in those grumbles. -2 times -4, 2. Okay. And then we multiply these out and combine them to get whatever my vector is corresponding for. The transformation of -7, +7. Does that make sense? Any other questions? Yeah.
So really quick, I don't have to work it out, but like, if the matrix is like n by n,
Mhm.
is the degree of the polynomial always going to be?
Yes.
that?
Yes. Yeah. Any other questions before we break? All right. Good luck to all of you taking the exam tomorrow. For those of you online, good luck. Whatever semester you're watching this.